The 18 electron rule is a useful rule of thumb in coordination chemistry that allows us to predict the stability of transition metal or coordination complexes. In essence, what we would be looking for is to see if there are 18 electrons surrounding a transition metal. And if so, then it's likely that that coordination complex is going to be more stable. Now, of course, there are some exceptions, but as you'll recall, this is a very similar rule to the octet rule that you would have learned about in previous chemistry courses. Recall, for example, when dealing with molecules that contain carbon or oxygen, for example, these nonmetals have access to valence orbitals like the s and the 3 degenerate p orbitals. In each of these orbitals, we can place 2 electrons, each with an opposite spin, and since we have 4 total valence orbitals, this would allow us to have a total of 2 plus 2 plus 2 plus 2 is 8 electrons. Now consider, for example, something like a transition metal. Transition metals contained in the D block or the center of the periodic table don't only have access to those s and p orbitals, they also have access to the 5 degenerate d orbitals. These d orbitals are going to be the dxy, the dyz, and the dxc, the dx squared minus y squared, and the dz squared orbitals. Now, as you can see, we still have those same 4 orbitals that we had for nonmetals like carbon and oxygen, but we also have these additional 5 orbitals that can contain a total of 2 electrons in each of those orbitals. Now, instead of having just this original 8 electrons that gave rise to the octet rule, we have this additional 10. 10 plus 8 electrons gives rise to the name 18 electron rule. Transition metal compounds can oftentimes be far more complex than the types of molecules that you've seen previously. To account for this, we need to reconsider the way that we count the total number of electrons surrounding an atom. Here is a step-by-step tutorial for how to do the neutral ligand or covalent method to counting electrons. In a subsequent video, I'll teach you about the ionic method. Step 1 is going to be to count the metal valence electrons. So, for example, titanium has 4 valence electrons, cobalt has 9 valence electrons. The second step will be to identify the electron contribution that comes from the ligands. Now, there are basically 3 different ways that we can consider this. Ligands can have sites that can contribute 2 electrons to the transition metal, 1 electron, or even in some cases 0 electrons. When we consider these different types, we'll call this X and L type ligands. We'll talk about this further later in the video, but a couple of examples of this are going to be, for example, carbon monoxide, or the carbonyl ligand, is an L-type ligand, and that means that it contributes 2 electrons to the coordination complex. The other type that we will focus on here are going to be X-type ligands, and an example of this would be fluoride. The fluoride ion can act as a ligand that supports transition metal complexes, and this is going to be an X-type ligand. X-type ligands contribute 1 electron to the overall electron count. Now we need to move on to considering the overall charge of a complex. Transition metal complexes, similar to small molecules, can be ions. They can be cations and have a positive charge, which means we would need to reduce the number of overall electrons that we account for, or they can be anions and have a negative charge. This would mean that we would need to contribute more electrons to our overall count. And then also, a new type of bond that you're going to learn about in this class is going to be metal-to-metal bonds. Metals can, in fact, bond in several different ways. When we consider metal-to-metal bonds, we need to basically take one of the electrons and give it to one of the metals, and the other electron in that shared bond would go to the other metal. And then that way we can account for our overall electrons. And then the last step is to take the sum of all of those steps. I think it would be useful to show an example here. So in this complex, we're looking at iron is the transition metal. there are 2 chloride ligands and 4 ammonia or amine ligands, as they're known in the nomenclature for coordination complexes. So iron, step 1, count the total number of valence electrons. For iron, it's going to be 8 because it's the 8th element on the 4th row of the periodic table. So we will have 8 electrons coming from iron. The electron configuration from the ligands, since we haven't reviewed it yet, I'm just going to tell you, chloride, similar to fluoride, is an X-type ligand. So chloride is an X-type ligand. And ammonia, or these amine ligands, are L-type ligands. So ammonia is also an L-type ligand, so it contributes 2 electrons. So now we need to consider how many total electrons are being contributed from the supporting ligands. So since we have 2 X-type ligands, that's going to give us 2 electrons, 1 each. Again, X-type ligands contribute 1 electron to the overall count. And in this case, we have 4 amine ligands, or 4 L-type ligands. And since each one is contributing 2 electrons, that gives us 8 total electrons. The overall charge is 0 in this complex, so we do not have any electron contribution from the charge. We don't have 2 metals, so we don't have any metal-metal bonds. So again, we don't need to consider metal-metal bonds here. And now all we need to do is take the sum of all of these electrons. So 8 plus 2 is 10, plus an additional 8 gives us 18 electrons. So in fact, I would predict, based on the 18 electron rule, that this complex would be particularly stable. The 3 basic types of ligand interactions can be classified by the symbols L, X, and Z, which correspond to 2 electron donors, 1 electron sharers, and 0 electron contributors to the overall electron count of a transition metal complex. A simple frontier molecular orbital approach can be useful to understand the type of interaction that's happening between the ligand and the metal for each of these types of ligands. Consider, for example, an L-type ligand, where the ligand is acting as a Lewis base or a 2 electron donor. You have a orbital from the metal that is empty, and a ligand orbital which is filled with 2 electrons. These electrons are donated in a way to create what's called a dative or coordinative bond. So as you'll recall from your molecular orbital theory, this would generate a new bonding molecular orbital where the 2 electrons are coming from the ligand and thus contain mostly ligand character. So this is what's known as a dative bond, where the electrons are coming from the ligands to the supported metal. X-type ligands are 1 electron contributors, which are much more similar to the typical covalent type of bonding that you're probably familiar with, where 1 electron each is coming from the ligand and the metal to create the new covalent type of interaction, or a 1 electron sharing between the metal and the ligand. A Z-type ligand is a unique and far less prevalent type of ligand, where all of the electrons are actually coming from the metal, which seems counterintuitive because typically when we think about coordination complexes, we think about them in terms of Lewis acid-base chemistry, where the metal is a Lewis acid. However, when you have a ligand that isn't contributing any of the electrons, then you end up flipping that. And a common example of this would be BF3, which is a Lewis acid that is electron deficient and is not going to contribute any electrons to the overall count. And this is where the designation popularized by Malcolm Green comes from when we talk about X, L, and sometimes Z-type ligands. Here are a few common examples of L and X-type ligands. The X-type ligands are similar to chlorides, fluorides, or other anions such as this methylene group. Additionally, L-type ligands oftentimes have either a lone pair or a pi bond to help you easily identify. So triphenylphosphine is an example, similar to amine, has that lone pair. Carbonyl is also an L-type ligand. We'll talk a lot about carbonyl in this class, especially when we get to pi back bonding. Ethylene is also an example of an L-type ligand. And notice that it does not have any lone pairs, and in fact, the interaction is coming from the HOMO of ethylene, which is going to be that pi bond. So what's interesting about ligands, and especially as we move into more complex ligand structures, is that they don't have to just be one of these types. In fact, as you can see here, there are examples where they can contain multiple types in the same ligand. This is often going to be true when you have ligand structures that have what's called hapticity, or that they can bond through multiple atoms. This is often denoted by the symbol eta, with the number as a superscript indicating how many of the atoms are participating in that bonding. So here is an example of the allyl ligand, which would be eta 3, and this indicates a hapticity of 3. So all 3 of these carbon atoms are participating in a ligand coordination. The cyclopentadienyl ligand is going to be eta 5 because it participates through bonding at all 5 of those carbons. And another example would be eta 6 for the benzene ring. All right, so now let's talk about what type of ligand classification would these get. These would be LN-XY, but this is just these N and Y are just meant to depict how many of each is contributing to that type of ligand. So for the allyl ligand, we have a pi bond and this lone pair anion. So this pi bond is similar to the ethylene, which we said was an L-type ligand. And this anion over here on this terminal carbon is similar to the one that we saw in this methyl anion. So that could help you predict that this is going to contain an L and an X. So this would be classified as an LX type ligand. Remember that L-type ligands contribute 2 electrons to the electron count, and X-type ligands contribute 1 electron. So therefore, we would expect that an LX type ligand would contribute 3, 2 for the L portion and 1 for the X. The cyclopentadienyl group is a very common ligand that we'll encounter, especially when we talk about sandwich compounds like ferrocene. It's eta 5, and notice that it has 2 pi bonds. So I immediately know that it's got 2 L-type portions to this overall ligand. And it also has this anion with the lone pair. So in fact, this is an example of an L2X type ligand. So when considering how many electrons that contributes to a complex, this is going to be 2 for each L, which is 4, plus 1 for the X, which is an overall 5 electrons. And finally, for benzene, we see that it has 3 pi bonds. So I'm going to predict that that's actually an L3 type ligand. Each L contributes 2 electrons for a total of 6 electrons. Now let's put all this together and see if you can count the total number of electrons for these 2 complexes. So remember that the first step is to determine the total number of valence electrons for the metal. The second step is to figure out the electron contribution from the ligands. The third step is to determine if there's a charge to account for that. The fourth step would be to see if there's a metal-metal bond, and then finally take the sum of all of those. So before we begin, I'm going to remind you, just because I know that you've just recently been introduced to these ligand types, the cyclopentadienyl, or CP, is an L2X type ligand. Each of the COs are L-type ligands. And over here you also have 2 CPs. So what I'd like you to do now is pause the video, because you learn by doing. Pause the video, see if you can count the total number of electrons for each of these compounds. And then resume the video to see if you figured it out. So pause now. Alright, hopefully you gave that a shot. And now let's go over the answer. So both of the metals in each of these complexes are manganese. Manganese is the 7th element on the 4th row of the periodic table, so it has 7 valence electrons. Same is true on both of these complexes. 7 electrons coming from manganese. The next step is to determine how many electrons are coming from the ligands. In the example on this side, we have 2 CP-type ligands, or cyclopentadienyl ligands, which, as we said, are L2X-type ligands. That means that they contribute 2 for each of the L portions, and then 1 for the X portion, for a total of 5 electrons. So since there are 2 CP ligands, that means I have 2 times 5 for a total of 10 electrons coming from the ligands. On this side, we have a single CP ligand, which again is 5 electrons. And we have 1, 2, 3 CO ligands. Remember that CO is an L-type ligand. That means from each of these, since we have 3 COs, that we have 3 times 2 for a total of 6 electrons. So on this side, we have 6 electrons coming from the carbonyl ligands and 5 coming from the CP ligand. This is going to give us a total of 6 plus 5 is 11 electrons just coming from the ligands. Neither of these complexes have a charge. We'll get to some more examples of those soon. That means we can put a 0. There are no metal-metal bonds in these complexes, so again, 0. So if I add 7 plus 11, we would get a total of 18 electrons for this compound. And 7 plus 10 would get us to 17 electrons for this compound. One of the things that makes the 18 electron rule so powerful is that it can allow us to predict the reaction mechanism, or the pathway from which we can convert reactants to products. On the board is an example where you have compound 1, which has a total of 16 electrons. 16 electrons, which is a perfectly stable molecule for square planar D8 complexes like this. And the product is also 16 electrons. And what you see is that the starting material 1 can be converted to the product 4 through one of 2 ways. It can follow a dissociative mechanism, dissociative because one of these ethylene ligands dissociates from the coordination complex to create compound 3. Or we could proceed via what's called an associative pathway, where carbon monoxide or carbonyl ligand associates to an open coordination site on the palladium metal. Subsequently, we can achieve the product from either pathway. Either pathway can help us to achieve the product. So, how do we know, or how can we use the 18 electron rule to predict which pathway this reaction is going to progress? So, we can figure out how many electrons are contained in this coordination complex and how many for compound 2. So we do the same as before, the number of valence electrons for a metal. In this case, palladium has 10 electrons, 10 valence electrons for palladium. Each of the chloride ligands are X-type ligands, and the ethylene is an L-type ligand. So one L is 2, 2 X's is an additional 2, so that means that we have 4 more electrons, which means that overall, complex 3 only has 14 electrons. This one only has 14 electrons. Now let's do the same for compound 2. For compound 2, we still have palladium as the metal center. This has 10 valence electrons. Now we have 2 ethylene ligands and a CO, all 3 of which are L-type ligands. So 3 L-type ligands gives us 6, plus 2 X-type ligands from the chloroligands. That gives us a total of 8. So 8 electrons added to this gives us a total of 18 electrons for compound 2. This compound has 18 electrons. Now, as you recall, the 18 electron rule says that transition metal or coordination compounds that are surrounded by 18 valence electrons tend to be more stable. Therefore, we can predict that this reaction mechanism is most likely going to be associative because it follows a pathway that the intermediate is an 18 electron species.